So next up we have Andrew Walker. He's a Melbourne-based software development, a recovering academic, and he's going to solve, hopefully forever, a problem that we all have, and that's finding those little snippets of academic code online and actually getting them working. All right, good luck.
Before I dig too deep into how you might actually go about doing something like that, I think it's worth talking about what makes scientific software different. That'd help. Thank you.
Scientific software is absolutely different. Often the tools that we're actually using as scientists are commercial or they're quite expensive. And so as scientists, that means we have some quite challenging integration problems to deal with. How do you get those complex systems where you need them, and how do you make them scale over the range of tasks that you need to solve? So we solve problems from how do I solve this one thing in my interactive notebook to I have a processor for my group, how do I actually solve problems on there, all the way up to massive distributed computing problems. So one of the other big problems that Robert alluded to is about scientific software is definitely written by scientists for scientists. And so the expectation is that you have some understanding of the domain that you're actually working in, whether that's science or mathematics. But the final part of this is that it's just hard. So I want to talk a little bit about my research and what inspired this talk and the disaster that meant that I needed to come and do this. So I finished 2 papers with some collaborators talking about conformal mapping. So a conformal map is a function in the complex plane, and you end up with things like this. So you're transforming domains from one class to another, and you can do all kinds of impressive things. As far as I know, there are only 2 really well-known packages for doing that, and they're both written in MATLAB. One of them's a re-implementation or a future re-implementation. So I thought, okay, it can't be too hard. I'm a Python programmer. I understand most of the maths that underlies some of this. So I'll just go and rewrite it from scratch. You know, obviously, some of the best success stories in the Python community, NumPy, Matplotlib and SciPy, have been about re-implementing things that existed elsewhere. So I started my port, and then after the first week in my spare time, I'd kind of completed the basic object model inside the library, and I'd written all my lovely tests. Then the second week, I kind of ground to a bit of a halt and managed to finish porting 5 files when I had to do a deep dive into some of the spline code and sparse matrices and complex numbers. The next week, I finished 1 line. This is an overestimation. It was actually 1 character on 1 line. So I had a conjugate transpose that I didn't realize what it actually was. But this is one of the reasons why you don't want to have to do this from scratch every time. So most software engineers know about this idea of not invented here syndrome. So Python is a great language to do everything in, but science in particular. But sometimes it's a bit too easy to just assume that everything else that's out there doesn't fit your needs. So what choices do you actually have at the moment for interoperating with software written in other languages? We have things for interoperating with many languages. We have tools for interacting with things on the fly. We have tools for interacting with Fortran. We have more tools for interacting with C++. But for me, the most frightening thing is, how do I know where to start? And my advice to you is to understand the basic themes that exist in these sorts of tools and to keep calm and reuse stuff. One of the things that we're taught is to stand on the shoulders of giants. Make use of the software that's out there already and leverage off the work that other people do. So at the moment, I see two main reasons to learn about interoperability. The first one has been, Graham mentioned earlier from Ed's slides, is about performance. Now, this is definitely not a performance talk. If you want to learn more about performance, have a look for Ian Osveld's talks online. He's co-authored a new book, High Performance Python. You should definitely check this out. I'm more interested in this case of necessity. How do I integrate with packages written in other languages to make sure that I'm not the one who has to expend the effort or the money on maintenance and quality. So, this is a recent quote or a paraphrase of Travis Oliphant from Podcast.net, one of the new Python podcasts. Python's strength is that it's like software superglue. It lets you build abstractions like they're Lego. And that's certainly where most of the wins in the Python scientific ecosystem have come from. So you're pulling bits of, if you don't have to dig deep into something like SciPy to see some Fortran, to see some C, and to see some C++, and to see those things come together in one place. And that's where Python really shines. So the second part of my talk is a whirlwind tour of some of the interoperability tools that are out there at the moment. So I'm going to start with the simplest possible thing that might work, and we're going to start in the Python standard library, and we're going to gradually build up to more and more complex examples. So who's used subprocess? Just a show of hands. Pretty much everybody. That's exciting. So subprocess has been in Python since version 2.4, and it's about interoperability via subprocesses. So it's very convenient that my next example has been introduced in the last talk. So you saw some tree diagrams from classifiers. So this is a format called graphviz.dot, and so you can see a textual representation. So the classifiers that were talked about that were producing the feature trees will output to some text representation like this, and I can run some tool to actually get a picture out. So definitely talking about theoretic graphs here. And if I want to actually invoke dot, it has a command line API, and Python really shines at doing things like stuffing strings into command lines. So I can actually use some string formatting tricks to actually populate the arguments to my command line application. And I can use my local environment to actually fill those out. So this starts looking very similar to what you might write in Bash if you were writing an equivalent Bash script. But even nicer, the new check call that's in subprocess will actually ensure that if your subprocess returns an error code, so if it doesn't return 0, it'll convert it to a Python exception. So this becomes very convenient code. This is probably not the type of thing that you would want to use in production. There are better tools out there for interacting with GraphViz, but it certainly demonstrates what it's possible to do if those tools aren't available. So, subprocess is definitely the thing that you want to use if you're interacting with a tool that has a command line interface. And performance isn't an issue. So most of the time when scientists actually spin up external processes, they're starting long-running jobs. If you're starting lots of small jobs, you may actually want to look at other options. C-types is another Python standard library module, but this one, instead of interacting with whole applications, will let you interact with libraries. So in the research that I showed at the start, you saw some conformal maps. One of the things that you might want to do with conformal maps that has been a core part of the solution of partial differential equations And so normally if you need to do that, you would just import something like SciPy Special. And the reason that we have SciPy Special is because at the time SciPy was written, libc didn't actually include any functionality to call special functions. So that's all changed now though. C's actually improved and gotten a little bit better. So now I can do things like load a library on my local system, and I can get a handle back to that library, and then I can start actually importing individual functions. Now there's some really interesting Python magic going on here. It's actually looking up the attributes on the library handle and converting them back to Python functions. You can see it also converting argument types and the types, return types of the function. So C-types will actually make some pretty intelligent guesses for you about what you're trying to do. So once I've got those functions and specified the return types, I can just call them like I would any other Python function. So this is really convenient if what you've got is a C library that you want to call out to, and you don't want to know how the C code works, or you don't have a C compiler on the system that you're working on, which is potentially a case if you're involved in supercomputing. So my rule of thumb is use C-types if you only want one or two functions out of a library and you don't want to have to build your own wrapper. Even more so if you don't want to have to write some C code. C-types has a really big wall though. So there's a point that you'll get to with it where you just can't go any further. So you'll try and call a function that takes a struct of some kind, or you want to return a pointer to some strange allocated string. At that point, if it's non-trivial arguments or non-trivial return types from your functions, look at using one of these other options. So it used to be that SciPy included a really great tool for interoperability, SciPy Weave. It's since been refactored out and is now a library of its own that's available on GitHub. And it lets you take a string of C++ code and make it callable from Python. So I'm going to do the simplest kind of sciencey example that I could think of that demonstrates some of these ideas. So I've imported SciPy Weave. I've built up a string of C++ code, and I'm calling inline, and it will actually take a template of C++ code, insert the code in my string into that file, and then it will compile it into an extension module, and it will import it into the local namespace and call that function. So that the interesting things here though are that my argument to my function is actually being pushed out to the C++ code. So if you look at the there's some interesting bits here. So this A2 is actually my parameter, and the 2 refers to slicing in 2 dimensions. So there are some interesting little conversion semantics between Python and C++. So it's actually using the scxx library, and you can actually go and read all the code for that library. It ships as part of SciPy Weave. So one of the limitations of approaches like this are that you're relying on somebody else's interoperability layer written in C++ to behave correctly with Python. So here's another more extensive example of using SciPy Weave. Historically, I'm a robotics person, a motion planning person. One of the problems that we solve is it's called the piano movers problem. How do you move a piano through a room? And the trick to solving that problem is that you stop referring to the piano as a piano and you treat it as a point. And what you do is you make the walls bigger. And so this is effectively a geometric convolution. So you're moving one geometry around the boundary to enlarge the size of the obstacles. again, to the best of my knowledge, there are no libraries in Python for calculating Minkowski sums. But there's a really great C++ library called Seagull that actually has this functionality. And so here's some C++ code that solves this problem. You can start to see some newer C++ features if you read C++. So auto, and again, there's some of these interesting conversions that are provided by SCXX to make sure that the types that are being returned are actually Python types. So how does that look when I actually go and put the whole thing together? This is a far more realistic example of what you might do with this, by the way. There's the code that I had on the last slide. I've got another little string of support code. So if I want to call multiple functions from Seagull, I can share that code. Again, I've got my arguments that I'm passing in and out. I've got the headers that I need for this and my libraries. And unlike the last example with Seagull, with C-types, sorry, I've actually refactored out all my platform-dependent content into a function. So again, if you're going to do interoperability work, think about how you're going to use that code and share it amongst your colleagues. So for me, SciPy Weave is the right tool to use if you're integrating fragments of C++ code. So it's ideal if you found a library on the internet and you want to just copy the examples out and paste them into your IPython notebook or into your Python code because they already solve the problem that you want. It works best if you're comfortable with C++, and again, there are probably better solutions to some types of integration problems than just using SciPy Weave. So I try and focus on this if I'm prototyping. The output that you actually get from the tool is quite dense. You're actually compiling C++ extension modules on the fly. And so you'll have pages and pages of output that you have to deal with in your terminal. The other challenge is that you don't want to redistribute SciPy Weave code, one, because you need a C++ compiler, and two, because every time you run the code, you actually need to rebuild a new version of that extension module. And I would also say that perhaps avoid it if you're dealing with a lot of Python data structures. So if you're using a lot of NumPy, it's not too bad, but lists and tuples are a bit more challenging to wrap. Okay, has anybody used Python? Okay, so a handful of people. Python is a DSL for integrating C, C++, and Python. So it's not Python and it's not C++. It's some kind of hybrid. So here's another little example problem. I want the distance from a point to a line segment. So this has actually come up in more of our research. We were trying to do some conformal mapping on some domains, and we can write the code in NumPy, but it ends up being so ugly and so difficult to maintain that you really just want to write it how you want to read the code. So I stole some snippets of code off the internet that had that structure in the original C. But when you look at them in Python, you can see some of the commonalities with Python. So I've got function definitions, but I've got cdefs as well. So I can expose functions to just the C side of to the C part of the extension module. I've got some type annotations, so I can force the Python compiler to only allow NumPy arrays to be passed in. I can still throw exceptions. So when I ported my my C code, I actually had to return error codes. slightly more convenient. I can also add type annotations inline. Now this is very much suboptimal Python code. You can keep adding and adding type annotations, and Python has an inbuilt profiler as well, which is excellent for improving performance. But in this case, it was just enough to get the code running like this as a first pass. The next step is that I can actually write tiny pieces of Python code that will actually directly import C header files, and it knows how to translate those things into functions that are callable from Python. So my suggestions are, use Python if you're exploring a solution space. It provides the most seamless transition from prototype to something that you might ship on PyPy or on Binstar. Seriously consider using Python if you want to solve interoperability problems and you need to share your code. Again, the profiling tools are excellent. And my only issue with Python is that it's not C++ and it's not Python. It is its own language, and it has some interesting corner cases. So make sure that you've got enough time to actually learn it. So this is a different kind of approach to interacting with software written in other languages. A lot of what I do involves calling MATLAB from Python. And so if I had have actually been thinking this is what I would have done from the very start, I would have actually just called out to the MATLAB code that I needed to solve my problems for my research papers. The problems that we're solving look very much like this. They're like solving the steady state heat equation with conformal maps. You define some boundary, and then you tell the boundary conditions, you tell the solver what the boundary conditions are, and it knows how to solve the heat equation in those domains. Now, because there are such great tools in MATLAB for solving problems exactly like this, in the IPython notebook, I can load a magic, and I can set my boundary conditions, and then I can actually run a cell, and the code in that cell actually gets exported directly to MATLAB, and it will run as is. And so this image is actually a plot that's come from MATLAB back to Python. So this is a very convenient way to get access to other languages from Python. There are equivalent tools for interacting with R and a number of other languages from the IPython notebook. Okay. So my suggestion is to consider what options you have available to you when you go to interoperate with code written in other languages. Can you run an external process? Can you call an existing library? Or do you actually have to write a Python extension module? And if you do, which tool is the right tool to help you do that? When you do that, make sure that you're considering who you're actually writing that code for. So a lot of the time, if I'm writing code that I'm the only person who's ever going to need it, I effectively just want an IPython notebook. I probably want to do something interactively. If I need to put something on a group server or on a distributed computer, I'm going to want something that's a bit more reliably distributable. So I probably want some kind of package I could put on PyPy. Think about what dependencies are required. So if you, for subprocess, all I needed was the Python standard library. For C types, I've got dependencies on the system libraries. For SciPy Weave and for Python, I've got even more dependencies. So how are you actually going to manage getting those dependencies to where you're working? And always think about how much it's going to cost you to write and maintain your software. And again, keep calm and reuse stuff. Okay, thanks, Graham.
All right, thank you. Any questions? Yep.
Hi, so you didn't mention CFFI. Have you had any experience with that? I mean, it's kind of similar to C types in a way. You do need a C compiler, but
Yeah.
Just like to hear what you think.
CFFI is an important project at the moment, and it's really the only choice if you're interacting with C code from PyPy. It's likely to be the de facto standard way of doing interoperability in the future, but for scientists at the moment, I don't know whether it would be my first choice. You only have to dig into the setup.py of cryptography, which is probably the best known package that's using CFFI at the moment. It's not a task for the faint-hearted. There's probably a few days' work just to get something that's installable going. Yeah. There are also alternatives. So back on that very first slide with the big list of options, where is it? Reflex and CPP-YY are extra tools that will actually let PyPy interoperate with C++ code. So they're the future of the C++ interoperability from that standpoint.
All right. Any further questions? Yep.
Thanks. Just wondering how easy you found to port code from MATLAB to Python and the other way around.
Porting directly, very time-consuming and tedious. There are some extra tools out there. There's some packages like SMOP that will actually translate MATLAB code to Python. Perhaps not the cleanest Python that comes out of a tool like that. My suggestion is if you can call MATLAB directly, do that. But it's a challenge from a licensing standpoint, I understand that. But you have some choices. You can either translate or you can call out to MATLAB.
Okay. I've got a question. Are there any significant gaps you feel in interoperability and any sort of features or libraries you'd like to see?
I really do think that Python is blessed in the amount of effort that's been invested in solving interoperability problems. I think if there was one thing that I think that we're missing, it's a good set of examples about how to go and do that in a slightly easier way. So it would be nice to have some simple demo projects that took you all the way through setting up Python projects in particular. It goes from being quite easy in the IPython notebook to get something going to a little bit more tedious to get something that you actually want to publish on PyPy.
Yeah. That's something I found too, like getting the basics working is fine, but then it ramps up quite quickly.
Yeah. But I must say it's much smoother doing something like that than it is in C types, where you do tend to hit a wall.
Yep. Great. Just 2 more questions, and then we'll do lunch.
Thanks, really good talk. So for that PyMat bridge, what's the performance overhead of calling into MATLAB? So if you've got like a tight loop in Python, calling into MATLAB's not going to work?
Not going to work, no. So you would want to call your MATLAB APIs at the very highest level. So my very simple example only really works because I've got one function that's actually doing any work. The rest is just plotting.
Yeah, so I guess another thing might be to, in the other language, write like a little network server or something that you can, sort of ping it over a protocol and like kind of not integrate them and just do
Yeah.
network requests?
And that's exactly how this is actually working at the moment. It's opening up a PyZMQ connection and actually communicating backwards and forth over that channel. So the R connections, I believe, work the same way.
We're a little bit better for time than I thought, so yeah, we'll do one more question.
You listed Boost Python up there.
Yeah.
Have you done anything with that? My experience of actually using things that have been wrapped with that was that they were very easy to debug my use of it as compared to the others, but I've never actually built something with it, so I'm wondering what your experience with that's been.
I've used Boost Python a little bit. Perhaps not debugging as much into the C++ end of things. I haven't seen a huge number of big projects. There are Seagull wrappers that are Boost Python wrappers and Swig wrappers as well. Yeah.
All right. We have much more time. So, any further questions? No? Okay. Well, in that case, we'll go get some food. So, once again, thanks, Andrew.